A group is a mathematical structure consisting of a set G, a binary operation defined in G, and an element of G that have certain properties. Being a binary operation on G means that the dot, which is the notation for binary operation, is a function from x cross x, where x is actually G in our case, to G. And that means that every pair of elements of G will relate to a certain element of G called A dot B, which we sometimes also write as AB. As we said earlier, the third ingredient of the triple, the group, is an element of G. Now, the axioms that a group must satisfy are the following. Firstly, the binary operation must be associative, which means that for every A, B, and C in G, A times B times C must equal A times B times C. The second axiom describes the behavior of the element 1 in relation to the binary operation. It requires that for every element A in G, A times 1 must equal A, which must in turn equal 1 times A. There is also a third axiom that requires that for every A in G, there exists an element B in G such that A times B equals 1 as well as B times A. It can then be shown that B is unique for a given A, which allows us to adopt a special notation for B that only refers to A. We write B this way and call it the inverse of A. So a group is a triple consisting of a set G, a binary operation on G, and an element of G having these three properties. There are alternative ways of defining a group. Some authors prefer to include the information of how to get the B from each A, specifically the unary operation of taking the inverse, as part of the structure. So some authors will define a group as a quadruple, satisfying the same axioms, where now the third axiom will be restated in a simpler way as for every A in G, A times A inverse equals 1, and that equals A inverse times A. Other authors prefer to drop the 1 as well and just represent a group as an ordered pair consisting of the set G and the binary operation. So sometimes you will see group defined as an ordered pair. The reason why we can drop 1 and we don't have to include it in the structure is because it turns out that there will always exist exactly one element having the property 2. If you had another version of 1, let's say 1 prime, having the same property 2, you can actually show that 1 and 1 prime are equal to each other. It is for the same reason that here we dropped the part of the structure describing the inverses of elements. That's because for every A, one can show there is exactly one B for which this property holds. So that's why we didn't include it there. And then some authors go to a further extent not to include 1 either, because 1 is also unique. Now, further modifications can also be done to the properties themselves. It turns out that one of these two equalities and the corresponding equality here can be dropped. One can prove those equalities using the other equalities, which we're not going to do here, but it is possible to do that. So there are different ways of defining the concept of a group. The one presented here is one of the ways. There is also different notation one can use for the binary operation and the special element, which, by the way, is called the identity element of the group. Instead of using notation that resembles multiplication, we could also use notation that resembles addition. So we could define a group as a triple with plus in the place of dot, and then we would use 0 in the place of 1, because an axiom similar to this that is expressed using addition would now be saying, let's actually refer to the second one. We'll be saying a plus 0 equals a, which is more natural than to say a plus 1 equals a. Coming back here, similarly, we would have a plus a inverse equals 0. So then the inverse, obviously, would not be anymore power minus 1. It would rather be minus a. So for this notation, the inverse of an element becomes what naturally would be minus a. So this is just a notation, of course. In either of these cases, we do not insist that the multiplication and the addition are the usual multiplication and the addition of numbers, although they can be. And this would give examples of a group. For instance, we could take the set of integers and take addition of integers as the binary operation, and then the identity element would necessarily be the number 0, and there we would have inverses given by minus an integer. An example of a multiplicative group, where the group operation is represented by multiplication, this time the usual multiplication of numbers, would be if we take positive real numbers, that means not including 0, then the binary operation can be the usual multiplication of such numbers, and the identity element would be 1, the number 1. In this case, of course, the inverse will be 1 over a. For an element a, the inverse of a would be 1 over a. Why is that? Because a times 1 over a will equal 1, as well as 1 over a times a will equal 1. Both of these groups both of these two groups, the one with integers and addition and the one with positive real numbers and multiplication, both of them have an additional property of commutativity. In both cases, for every a and b in G, let me write it in a multiplicative way, a times b equals b times a. Using additive notation, of course, we would have written a plus b equals b plus a. Groups that have this special property, they're called commutative groups, or alternatively abelian groups. Not every group is abelian, though. Not every group has this property. A standard example of a non-abelian group would be the group of permutations of a set. We could consider a fixed set X, and as our G, the underlying set of the group, we could take that to be the set of all permutations of X. What do we mean by permutation? Well, a permutation is simply a bijection from x to x, a function from x to x that has an inverse. This is the set of elements of our group. What about the binary operation, we would take composition of functions as the binary operation, applying one permutation and then another. The identity element of that group will be the identity permutation, the one that maps every element of X to itself. So this is typically written as 1X. What about the inverse operation? The inverse of every permutation will be what it naturally would mean. The same permutation, but in reverse. So basically, if my permutation is a function from X to X, then its inverse will be the opposite function, the function that is the inverse of that bijection. These groups are not commutative unless X is very, very small. Like, for example, if X is a set having just one element, then there will be only one permutation, the identity permutation, and in that case, commutativity will trivially hold. But when X is a set having more than two elements, then this group is no longer commutative. For example, if X has three elements, we can view a permutation of three elements as a symmetry of a triangle. We take a triangle and we try to match it onto itself in different ways. One way is to flip along this axis. Another way would be to rotate. Let's label the vertices of the triangle. So the flip will be represented by the permutation that maps A to C, keeps B at the same spot, and maps C to A. Think of this as one element of G, as one function from our set X to itself, which in this case is the set of elements A, B, and C, where all A, B, and C are all different from each other. And then consider another permutation, rotation. This one would map A to B. It would map B to C. So let's say we consider rotation in the clockwise direction. C would be mapped to A then. And after that, we can compose these two permutations in two different ways and see whether we get the same result. So to do that, let's redraw them here separately. Let's say I first apply the flip that keeps B at the same spot and swaps around A and C. So that's applying this permutation, and then I compose that permutation with the other one. So then A will map to B, B will map to C, and C will map to A. So the A here will map to B, B will map to C, and C will map to A. In fact, maybe it's better to write it this way. Let's keep A, B, and C in the same order in each case. So the flip keeps B at the same spot and swaps A and C, whereas the rotation maps A to B, it maps B to C, and then C back to A. Composing these two permutations amounts to just tracing the arrows, which will give us, so by the composite of these two permutations, in other words, by multiplying them in the group we are building, A will map back to A, B will map to C, and C will map to B. Now, if we compose them in the other order, if we first applied the rotation, so let's write out the rotation once again. A maps to B, B maps to C, and C maps to A. And then we applied the flip, where A and C swap, but B stays with B. This time, if I follow the arrows, I get A is mapped to B, B is mapped to C. I should rather write this in the same style as before. ABC, ABC. So once again, A maps to B. B maps to C. And C, sorry, there was a mistake here, right? There should have been A. So B maps to A, not to C. And C maps to C. You see, we get a different permutation. So if I represent this permutation by X and that one by Y, here we'll have Y first and then X. Then this permutation is the composite of Y and X, which we write in reverse order, as with composition of functions. So Y composed with X equals that. On the other hand, X composed with Y equals this. And we see that they're not the same, because the permutations are indeed different. So X composed with Y is not the same as Y composed with X. This shows us that composition of permutations doesn't have to be commutative, and indeed it isn't in this case. So this additional fourth axiom, which defines an abelian group, doesn't hold. So not every group is abelian, even though these groups of numbers with addition and multiplication, they were abelian. We have now another group that is not abelian. The group here can be generalized to symmetries of a shape. Here we had a triangle, but one can consider other shapes and look at various ways the shape can be matched onto itself. Describe that to be the elements of your group. They will be called symmetries. Then one can show that because composition there, the multiplication there, it reduces to composition of functions, one can show that the group laws will hold. And so we get group called group of symmetries. So back to the question, what is a group? Group is a mathematical structure consisting of a set G, a binary operation on it, an element of it, a special element, satisfying these three conditions. And as we saw, there are many examples of such structures. They arise in various places. They arise in number theory. They arise in geometry in the form of symmetries. But these are not the only examples. There are also other examples of groups. Groups are very important in physics and other applications of mathematics, as well as in mathematics itself. A large part of mathematics deals with either the study of groups or application of such study, or abstraction of various properties of groups to other mathematical structures.